Here we'll look at how to graph functions or how to interpret a function from a graph. Okay, now then, sometimes you're going to want to write a rule for a function. For example, this one right here. Hopefully you remember from pre-algebra that you can write it using y equals mx plus b, the slope-intercept form. If you remember that, you can extend it and see that the intercept would be at 5. Now notice that when you do this one, the vertical is progressing 5 per box, but the horizontal is progressing at only 1 unit per box. So you'll need to account for that when you count your slope. So from here to here is up 5 and over 1, so this is a slope of 5, rise over run. So the equation for this would be 5x plus 5. You can see that the intercept would be right there. So this particular one would be 5x plus 5 y equals 5x plus 5. Now let's identify the domain and the range. Since we've only been given these 4 specific points as our function, we only want to know these 4 specific points. Well, let's see. The domain, remember, is on the x-axis. So here the domain is 1, input, output, range is 10. That point is 1, 10. This is the element of the domain. This is the range. So we can also look and see all of the places that are domain, x values. That's 1, 2, 3, 4. So all of the domain will be 1, 2, 3, 4. Let's look at the range. What will all of the range be? Well, let's look over here. On the vertical axis, the y value is 10, 15, 20, and 25. We don't want the extra values because we were asked only for the domain and range of the function that's represented by the dots. So then this is an equation or a function rule written for this set of dots using slope-intercept y equals mx plus b. Or you could rule out the points and just guess and check. Then we've identified what are the asked for domain. What are the x values of each one of these points? Just kind of look down at the x-axis. What are the y values of each one of these points? Look there. So there we have that. Okay, so now let's go to what it looks like on a graph. Okay, it's really easy when you have a graph to see if it's a function. So let's do some here. Here's a little simple graph. I'll mark out some units. And I'll just put some dots in. So I'll call this one A, I'll call this one B, and I'll call this one C. So as we look at this, let's say, is this a function? For every member of the domain, is there uniquely one member of the range? Okay, whenever the domain x is 1, we go up and we see that there's 1 point and the range is 4. Okay, there are no others. When the domain is 2, we see the only point is at 1, so that works, and 4 to 2. So that works just fine. This is a function. Now, what if I happen to add a point D here, and this point is at 1, 1? Okay, now look what happens. When you have the input 1, there are 2 possible outputs. So if Froggy says 1, then Doggy might say 1 or Doggy might say 4. It is not reliable. To be a function, whenever you have a particular input, you must have only one choice for an output. So what we see here is that this is not a function. And it's really easy to see because the A is right on top of the D. Whenever you do any function, or any possible function, and you see that something is exactly on top of something else, it is not a function, and it will not be. So with a graph, it's really easy to see once you've graphed it, is it a function or not? This is not a function because the point A is physically above the point B, which means, in more mathematical language, that for every input, the input 1, it's not unique. There are 2 outputs. Therefore, this is not a function.